Good afternoon, everyone. I am Farhad Salimi, and I'm a postdoc at CAR, and I'm going to host today's webinar for all of you. I would like to thank you all to join in to today's webinar, and we have a special guests today that they have linked directly from Peking University. I would like to thank Zoran Ristevsky for organizing that. So I would like to welcome all the people from China and say hello to all of them. And so I will start with introducing our presenter today. Presenter today is Dr. Svetlana Stevanovic from Deakin University. She's a lecturer of environmental engineering and has been the leading research on the measurement of the oxidative potential of airborne particles in Australia. Her research is focused on the chemical characterization of OP in gas and particle phase, secondary pollution, combustions, emissions, and future fuels. Her presentation today, as you can see on your screen, is titled An Instrument for Rapid Quantification of PM Oxidative Potential Particle into Nitric Oxide Quencher, PINC. Can I ask you all to keep yourself mute while Svetlana is giving a talk, and at the end of the webinar we have time for questions, and it would be the best if you use that chat box to type your questions, then Svetlana would read aloud your questions and answer. So Svetlana, the stage is yours, we're listening.
Thank you everyone for coming. So today I'll talk a bit about oxidative potential, about methods that are used for the measurement of oxidative potential, and then I'll talk about the instrument that we have been developing over the past, I guess, 6 years. Now it's done, and I'll show you some of performance characteristics of the instrument and some preliminary measurements. So, okay. So now I will just start by briefly describing the air pollution, defining it. As you know, it is responsible for more than around 7 million premature deaths each year. Air pollution is composed of gases. So as you know, we have unburned hydrocarbons, NOx gases, NO and NO2, carbon dioxide and monoxide. And apart from that, we have particulate matter. Particulate matter has been linked to cardiovascular diseases, different lung conditions, cancer, in general, increases in prevalence of chronic respiratory diseases, as well as adverse health effects in both embryonic and adult neuron activity. Definitely studies have shown a link between the exposure of particulate matter to diesel exhaust and increased lung cancer, and as a consequence of that, diesel exhaust was classified as a carcinogenic by the WHO. For example, diesel exhaust is an example of primary source. Unfortunately, it is more complicated than that. So we have atmospheric pollution coming out from primary sources, which are they can be mobile or stationary combustion sources, and mainly we get different volatile organic compounds and soot. We have natural sources of pollution like bushfires, vegetation, sea salt, mineral dust. Once they are all in the atmosphere, they get further transformed by atmospheric oxidants, for example, hydroxyl radicals, ozone, SO2, NO2, peroxyl radicals, ammonia, nitric acid, etc. And it all leads to the formation of secondary organic aerosols. And normally, we are dealing with secondary pollution, not the primary one, and that's why it is really important once we do measurements to get a good time resolution so that we can actually estimate the toxicity of a particular source, not the transformed source, because again, secondary pollution is going to be the result of aerosol mixing, of aging, of further chemistry and long-range transport. So why are atmospheric particles important? They are important due to their health effects and their effects on climate. What are the challenges associated with atmospheric aerosol chemistry is that particles are too small. Collection, we have problems with collection and then detection and further analysis, and then how to link it with real toxicity and how to link it with human toxicity. So we know so far that health effects due to the exposure of particulate matter are linked to decreased lung function, increased respiratory symptoms, increased chronic obstructive pulmonary diseases, increased cardiovascular disease, and increased mortality. We also know that there are strong correlations between them, but we know little about it. Exposure-response relationship, particularly for smaller particles from epidemiological studies. And also we know very little about mechanisms by which particles induce these health effects from clinical studies. We just have some assumptions I will talk about, some theories that are existing. But one of the most important aspects here is that size does matter. So fine and ultrafine particles are particles smaller than 100 nanometers, and even smaller than 50 nanometers. These ones are considered the most toxic ones, and they may be the cause of production of reactive oxygen species. Now, reactive oxygen species or ROSs are thought to be the reason for the oxidative potential and then further toxicity of particulate matter. Particles like gases are characterized by their chemical composition, and their chemical composition is usually expressed in milligrams per cubic meter. But unlike gases, particles also have a characteristic size. And that size is important for lung deposition. The smaller they are, they can penetrate deeper. And for atmospheric transport, so the smaller they are, as you can see, these are just comparisons of particles that we are dealing with. This is sand here. Sorry, this is sand grain, this is boulder, this is petrol exhaust particle. And I don't see what is on the right, but probably it is dust particle on the right, I think it is. So as you can see, smaller particles that we are dealing with, they will stay longer in the air. If they stay longer in the air, they will have time to transform further. So they will be, for sure, secondary particles more than larger particles. As you can see, 1 micron particle will stay in the air for around 300 seconds, 10 micron particle for around 3.2 seconds, while big particles like 100 micron particles will just be in the air shortly, and then they will settle down due to gravitational settling. If the density of these particles is larger, their time in the air is shorter. So particles of higher density will settle quicker. Regardless of that, as a conclusion, we can understand that smaller particles, apart from being able to penetrate deeper in lungs, they are having larger surface area for reaction with our lungs, and also they stay in the air for longer time, so that they are prone to further transformation, and we can breathe them definitely for longer time. There are different hypotheses that are used to explain the negative health effects caused by particulate matter, but one of the leading theories are that inflammation and irritation of the epithelium are causing these respiratory and lung function symptoms. So during the inflammation, we have release of a mediator, which is then leading to increased blood coagulability and then cardiovascular problems. Then during direct penetration through epithelium, we have again increased blood coagulability and cardiovascular problems. One widely accepted hypothesis for PM injury states that PM is able to induce oxidative stress in lungs. Now, oxidative stress is defined as an imbalance between the production of reactive oxygen species and the cells or our natural antioxidant defense. So this is that balance. As you can see, we are having free radicals in our body. They are necessary for the functioning. And also we have antioxidants that are controlling the balance of free radicals action. Now, once we have more of free radicals than antioxidants to fight against them, we will have oxidative damage or oxidative stress. Oxidative damage will attack key molecules like lipids, proteins, nucleic acids, and it is going to lead to either tissue injury or inflammation. And if this oxidative stress is prolonged, eventually it can lead to apoptosis or cell death. So oxidative stress activates certain signaling pathways, and they are subsequently activating inflammatory responses, and then, uh, as I said, they can lead to cell death. Why this is important is that recently it has become evident that those particles have those particles, meaning particles coming from the pollution, they have the ability to generate free radicals and related reactive oxygen species like superoxide anions, hydrogen peroxide, hydroxyl radical, organic peroxides, etc. And their action is in the exact manner by which we have described what is happening when we have an abundance of ROSs. But still, the very mechanism is not proved and not completely understood. It has been recognized that the organic and metal PM components can induce pro-inflammatory effects in the lungs due to their ability to cause oxidative stress. And more or less, that is what we know so far based on clinical studies. What is important is that particles can either carry ROS on themselves, it's called exogenous ROS, or upon introduction of particles into our cells, then cells can generate ROS and it is endogenous ROS. So regardless of that, we are actually talking about oxidative potential. Oxidative potential would be a metric that we use to demonstrate the potential of particles to cause negative health effects or to cause that oxidative damage. Now, how we detect the ROSs in particles, the only analytical approach that permits the direct detection and quantification of free radical species is electron paramagnetic resonance, or EPR. This method has limitations as it is a very complex instrument, it's very expensive, the sensitivity is low, and short radical lifetime prevents its detection. So, and it can't be operated in field, so it is pretty limited. And also, if you collect particles, let's say on filters, then the usage of EPR will be limited to those persistent free radicals with high lifetimes. When we sample ROSs, we are basically facing three challenges. So the sampling time that is necessary so that we can see a signal or that we can observe a change. Preservation of chemical species is a big problem, as we said before. Once pollution species, meaning volatile organic species and particles, once they are released in the atmosphere, they start to change. So to preserve chemical species in their original as original component, it's very hard, and that's why many sampling techniques are limited as they can't provide preserved chemical speciation. And also detection of all relevant ROSs. That's the third and most important challenge, is that as I will talk now, for the detection of ROSs on particles or ROSs in atmospheric pollution in general, we are using chemical methods, cell-free methods. These are molecular chemical probes that are normally working on the principle of fluorescence detection. And every probe is sensitive towards different species, and none of the probes can detect all the ROSs, and that is one of very important limitations of existing ROS measuring approaches. Still, fundamental uncertainty and disagreement persists regarding the following question. What physical and chemical properties of particles can impact health risks? Is it only ROSs? Is it also the size of particles? Is it the charge as well? What pathophysiological mechanisms are operative? And what air quality regulations should be adopted to deal with the health risks? So these are still very important questions that we need to address in the future. I will start with important findings to date. So I will talk what I have been doing and what we have discovered as a research group about what is influencing oxidative potential, whether oxidative potential is ultimately coupled to the structure of respective molecules that constitute the fuel or any other source that will burn, like wood or plastic or waste. And then also I will just briefly talk why is also the volatile organic component, the gaseous component of pollution important apart from particles. Um, so what we have discovered, this is an experiment that I'm showing done by Branka Miljevic in Switzerland. So this experiment is actually showing that, as we know, organic compounds are very important for the toxicity of pollution. So that ROSs are mainly organic species. And that toxicity caused by particles will be contained in the organic phase. But what I have discovered during my work is that it is not that the entire organic phase is going to be a source of ROSs, and also not every organic fraction is going to be equally potent to cause any oxidative damage. This experiment was designed so that we can analyze, let's say, different burning stages. So cold startup of burning wood, then cold stable, then the warm start, and then when the last one here, as you can see, is when the burning of wood was stable. On y-axis, we have ROS concentration that is actually telling you again about the potency to cause the oxidative damage. And we can see that the most toxic stage of burning wood is that called stable start. So basically, maybe a few minutes after we make the fire. And firstly, once she tried to just relate the measured oxidative potential during the whole burning event, she couldn't, and with organic composition, with the total organic content, she couldn't actually see a good relationship. But once she broke this burning event into different stages of burning and related that with the measured toxicity in different stages, she got a wonderful relationship. So, and as you can see, during the cold start, which is considered as the most toxic component of burning wood, ROS increases 32 times with the increase of organic per mass. For warm start, it is 4 times, and for cold startup, it's 11 times, as you can see, based on these different B factors. This is additional graph that is demonstrating I was doing different fuels. Different fuels were just used to demonstrate the different composition of precursor of combustion. That was the easiest, and then I was just calculating the total organic component measured and relating it to the total oxidative potential, and the relationship was actually not good. It was all over the shop. That was just confirming the previous finding that it is not the total, the entire organic fraction responsible for the ROS and the oxidative potential, that there is a subfraction of organic fraction that is carrying this toxic potential. Further experiments were done. So we investigated the organic phase. So we broke it into two different fractions. One was oxygenated fraction. The second one was hydrocarbons. And then we were measuring the presence of oxygenated organic aerosols and the hydrocarbon-alike organic aerosols, and then comparing the concentration of these two with the measured oxidative potential. For this, we used aerosol mass spectrometer to get the concentration of oxygenated organic aerosols. We used the factor 44 here. So this is basically the concentration of CO2 fragment, CO2 that is coming from particles, not from the gas phase. And the marker for hydrocarbons here was a butyl radical, so 57 is the mass. So we were using the intensity of these peaks, and they were like indirect measure of the concentration of these species. And I'm going to show you the graph. So once we plotted the oxidative potential against F44, which is the measure of oxygenated organics, we got this very nice correlation. So oxygenated organic compounds are responsible for the ROS generation. That was a very, very important finding published in EST. The second important finding was that gas phase is also carrying oxidative potential. Gas phase or VOCs in the gas phase are normally neglected due to many reasons. It is believed that gas phase cannot cause the real damage because it can't get to lungs, and also simply it is not measured in real time, and it's not considered for in ROS measurements. So we did measure the ROS in the particle and the gas phase, and we were using different fuels. As a measure of different composition of fuels, we used one metric oxygen content of the fuel. And that was also one of very important findings, is that the composition of something that we burn, in this case it was fuel, it can be waste or let's say wood. So the composition of a burning precursor, especially oxygen content of it, is directly related to the toxicity. So the more oxygenated the fuel is, the more oxygenated any precursor that we burn is, particles are going to be more oxygenated, and as a result more toxic. As we said before, oxygenated organics are more toxic. So more oxygenated fuels are going to produce more oxygenated particles that are going to be more toxic. On contrary, the gas phase, corresponding gas phase, is going to be less toxic. So once we increase the oxygen in the fuel, due to the partitioning of species between the particle and the gas phase, more those heavier particles, heavier species are going to be to stay on particles, and thus we will have this increase in the oxidative potential, and at the same time the oxidative potential of gaseous species is going to decrease. And it is going to be like that for all the fuels with the oxygen content out to 15%. Above that, the situation changes because the combustion conditions are very, very different. And due to the complexity of the combustion episodes for these very, very oxygenated fuels, we actually didn't consider this result like above 15% of oxygen, so that is for a complete separate study. But partitioning of ROSs between the gas and particle phase is actually very important. Here you can see how they partition during the one driving cycle. So we tested vehicle emissions, and this would be a very rough representative of, let's say, real driving. European stationary cycle actually is not, transient cycle would be more representative, but this was easier for us to do in terms of ROS measurements. As you can see, as the oxygen content here increases, the oxidative potential of particles increase. At the same time, the oxidative potential of gases decrease. And for example, this would be a nice information to be used once new fuels are, let's say, being introduced, or if we control the composition of the waste that we burn and use for the future energy generation purposes. So if we use more oxygenated fuels, we are actually going to decrease the VOC toxicity, and by using filters and catalysts, we can even further oxidize these particles and remove them from the stream. So that may be one of the solutions for regulation. Now I'm going to talk about particle sampling approaches that we use for assessing the PM toxicity. So briefly, there are different approaches. Some of them are listed here. I'll show you another slide with more advanced instrumentation. So what is being used the most is filter collection of particles due to high sampling volume. They are very practical, they're cheap, they have excellent collection efficiency. The drawbacks with this approach is recovery of particles may be poor. Also, we have evaporation of semi-volatile organics and at the same time we had absorption of gas phase compounds. So what we said in the beginning, so that it's very hard to preserve the chemical species as they were once they were emitted from the source. Liquid impingement, I will show you how it functions. So actually we were directly collecting particles in a liquid, which was making it practical and easy to use. Unfortunately, the drawback of that approach is low and size-dependent collection efficiency for particles that are smaller than 500 nanometers. And as we said, this is the fraction, size fraction that we are concerned with, like below 100 nanometers. So because of that low collection efficiency, impingers are also not the most optimal solution. VACIS is an instrument made by researchers in the US, Ciutas and his research group. VACIS is simultaneously concentrating ultrafine and fine particles. The drawback of his approach is that it is not good for continuous sampling, and also it's not commercially available once if you want to buy this very expensive and complicated time-consuming experiment is involved with VACIS sampling. So we didn't consider buying that. That was another motivation why we decided to make our own. This is actually just showing you the collection efficiency of impingers. This slide is showing you the new instruments that are being used for RS collection. All of them are mainly steam collection devices. And they are actually very good because when in operation, a sample aerosol is continuously mixed with vapor, and then we have condensational growth, and that is done to achieve high efficiency collection of ultrafine particles. These grown particles are then collected into liquid with a very high efficiency through different wetted impaction methods. And the direct injection of this steam is allowing for high supersaturations with high flow rates. So for this reason, steam collection devices, all of them that you can see here, can achieve highly concentrated samples as the ratio of aerosol sample flow to liquid collection flow, and it can be further maximized. With different systems here that you see. Now the difference between them, more or less, they're all steam collection systems. They have different chemical assays that they are using for the detection. And as you can see, one of the big problems with them is that they can't sample insoluble particles. The problem with that is that most of the combustion we are concerned with is insoluble particles, so carbon-centered particles, and that's why it was the further motivation for us to develop a new instrument. So these are the probes that are being used for the detection of ROSs. So we have different probes. Some probes like POHPAA and ascorbic acid, they are only sensitive to narrow ranges of ROS species, and that makes them unsuited for quantification of total oxidative potential. DTT assay is commonly used due to its ability to simulate the reaction responsible for the generation of ROS when PM interacts with cells. And it is making them suitable assay for the quantification of endogenous ROS. However, some new developments in microfluidic sensors have more recently allowed for DTT measurements to be as low as 18 minutes, which is still very, very long. DCFH, this assay here is used in combination with horseradish peroxide catalyst, and it is currently the most commonly used ROS probe in the literature for the quantification of exogenous ROS. And this is due to its relatively simple fluorescence-based quantification, and it has potential for semi-continuous monitoring and sensitivity. However, DCFH is prone to several issues, including auto-oxidation upon exposure to sunlight and air, and also it has a high background fluorescence that is going up during the sampling. That is why so we have tried some of these probes. They were not good for the real-time application, and that's why QT researchers developed different probes that we were testing with our system. These probes are all, as you can see, nitroxide probes. So this part here, nitroxide part, is actually quenching free radicals, and molecule itself is non-fluorescent. Once this nitroxide part here quenches free radical, it becomes fluorescent. The part that is giving fluorescence to this molecule is this fluorophore here, so this anthracene-based fluorophore, or this phenanthrene-based here. And the principle, this molecule is non-fluorescent, although it has a fluorophore, because of this electron here on nitroxide, which causes intramolecular quenching. Once a free radical from the atmosphere, from the pollution, reacts with this molecule, that quenching is released, and we have fluorescence that we measure. So based on the fluorescence that we measure, we are reporting the amount, we are doing the quantification of ROS species. Now, another chemical problem of the ROS detection is the solubility of different probes. So we have to use different solvents. If we use water-based probes, then we are limited to oxygen species or reactive oxygen species that will be dissolved in water. So that is one of the most, the recent problems we were dealing with. The idea behind any good real-time ROS measurement technique is to trap the particles into the solvent directly. And then to have a solvent that is allowing different oxygen species to be dissolved and then to react with the main molecule. So this is how impingers work. I will show you how other collection, but all the other systems, like even these steam collection systems, will collect particles in some kind of a solvent. So principle is more or less the same. This was experimental setup that we used to test the probe to see if it actually reacts with ROSs. We use cigarettes as a safe source of ROSs. And we realized here that once we increase the number of cigarettes or the number of puffs, so when we give more of ROSs, we have linear increase in the fluorescence, which was a good test for the suitability of the probe. And then when we decided that we will use this probe for the detection, we actually started developing the system. This system here that is shown is called particle into liquid quencher. I called it pink just to be more girly, but it is actually quenching particles that are grown in the supersaturated part. And once they are grown in this insoluble aerosol collector here, we will collect them eventually in the cyclone, and then we will do the fluorescence detection. I will actually explain more. This instrument was designed to overcome the difficulty of collecting ultrafines with a high efficiency through mixing of the sample aerosol with steam. So we can see that we have an aerosol, we have a steam generator. and then they mix in order to create a supersaturated aerosol. The particles in this aerosol then undergo condensational growth, in which the particle is coated in a layer of liquid water, and it is actually forming a droplet, a liquid droplet, exponentially growing them in size. When we use them in the pink, these grown particles are collected with a high efficiency into continuously flowing solution of the ROS probe. So we have this vortex here, and we input the liquid continuously that is wetting the walls. These incoming particles are being caught in this vortex and being collected with a high efficiency. In this flowing solution of ROS probe in dimethyl sulfoxide, and we designed this collector to be resistant towards the DMSO. The reason why we use the DMSO is that our probe is soluble in the DMSO, and also DMSO is also a very important part of the chemistry of the detection of ROSs. Now we have this the whole part here we call growth chamber. It's an aluminum growth chamber, and as you can see here, we are cooling the mixture and allowing time for particles condensational growth to occur. The chamber is actively cooled with a liquid coolant to prevent any excess heat buildup in the system from the steam supply of the aerosol sample. We tried to do it with the passive cooling system, but it was less efficient. And it was not really good for some warm aerosol sources such as engine exhaust or high temperature ambient condition, etc. To mention here, this is solvent resistant vortex collector. In principle, the design of this system is similar to that of a mini PM cyclone. However, while the cyclone design focuses on the cutoff size and shape, this vortex collector is predominantly concerned with the formation of a stable liquid vortex within this cone. The collector dimensions, we spent a lot of time designing this part. It was really hard. So the surface finish, sample liquid temperature, aerosol flow rates, everything plays a role in determining the vortex formation. So it was really, we were tuning these parameters for like 3 years, I think. And this large range of parameters makes prediction of vortex formation difficult, necessitating a design which allows for a visual confirmation of vortex. So original version of this instrument was that we had a stainless steel vortex collector, but then we had to make it transparent, and so transparent fluorinated ethylene propylene cone was made, and this ensures the instrument is solvent resistant, and also we can monitor the formation of vortex and how so that we don't have any bubbles, etc. This device was chosen over simpler ones for 2 reasons. The first one was that vortex collector collects particles directly into the liquid rather than into continuously wet solid surface, which is the case when we use impactor plates. And this also allowed us to have a solubility independent particle collection. You saw that most of these advanced methods that are being released now are just good for soluble particles and not good for insoluble particles. So our system is actually collecting all the particles that we have found that are being emitted. And also the liquid vortex ensures that the collected particles is homogeneously mixed, which is good for the fluorescence detection. So I'm just showing here some of these particle mass collection efficiency. As you can see, so this part here, we are interested in this part here into ultrafine mass portion, because when we originally did the experiment with particle mass collection, it was really high, but it's because these bigger particles are responsible for the mass collection efficiency. And we were interested in the mass collection efficiency of ultrafine particles. So we repeated these experiments with larger ammonium sulfate particles, and then we removed them using the impactor, and then we were just sampling the ultrafine fraction. And what you can see is the average SMPS particle size distribution of ultrafine particles that we have collected over the sample collection period. And then the mass distribution we calculated from the fitted distribution. So we can collect uh, collection efficiency is high, so 80% of the total mass of the sample was ultrafine portion that we were collecting, and our collection efficiency was high, as you will see, above 99%. So these are the results. So we took into account everything, even the steam dilution factor. So here, this is a significant improvement over an earlier wetted watt cyclone design, which was reporting the collection efficiency that is greater than 88%. So our collection efficiency is, as you can see, above 98%. For all particle sizes apart from these ones, and 50 that are still above 80%. This is response time. This is very important metric when we talk about the utilization of this instrument for field measurements. So we tested response time and also time delay, because we have two fractions. We have particles and gas phase. We are testing the oxidative potential of gas phase by placing a filter in front of the stream. So we firstly do the whole aerosol stream, then we do the aerosol stream with the filter, and then we subtract the total minus the filter based one, and then we get just what we get from particles. But all the time we are recording the oxidative potential of both the total phase and the gas phase, so that we have both signals. The time delay is 6.3 seconds, and that is a factor that we included in our correction analysis. We have mixing time of 32 seconds, so we need 32 seconds to switch between the gas and particle phase and to make the signal stable again. This is how it looks like. So this is how our signal looks like. As you can see, we have a total phase, then we have a filtered total phase or a gas phase, and then this blue signal is the result of subtraction of total phase minus gas phase. Here you can see a nice signal. So this is fluorescence, this is the spectrum. So we are recording the spectrum at approximately 486.24 nanometers. This was not approximately, this is accurate, but this is like the fluorescent maximum. So we can use both peaks here of the fluorophore, the emission peaks, and this is how it looks like. So this is the number of counts, this is time, and so this is particle gas phase, particle gas phase, particle gas phase. So this is one real-time profile that we can now get with our instrument. I will finish with the future directions. So over the past decade, there has been a tremendous amount of growth in the number of analytical measurement techniques that are being developed to measure atmospheric aerosols, not just in the field of oxidative potential. We have different mass packs that are doing the gas phase, that are doing the chemical composition of particle phase, etc., even free radical ones. We have additional instruments that make rapid real-time measurements of particle interfaces, as well as pro-particle heterogeneous phase measurements. They are needed to understand the processes that are contributing to aerosol formation. Also, accurate information that we can get will ultimately allow for models to better understand and predict atmospheric aerosol composition and its toxicity, and in turn to understand the impact these aerosols have on our climate and on our health on global scale and on regional scale. So a combined effort is needed here between chemists and atmospheric physicists to understand these challenges. Of course, we have to work with epidemiologists and doctors and to compare our studies with some clinical trials in order to get a proper information and then to be able to prescribe interventions. and to make predictions. So that was it. Thank you.
Thanks, Svetlana. It was a very interesting presentation. So now we have at least 10 minutes for questions. So there are two options. If anyone has any question, you can unmute yourself and ask the question directly, or type your question on the chat box and I will read it loud. And it would be good if you can first introduce yourself and then ask the question. Zoran, if anyone has a question from Peking University, you can just unmute yourself and ask directly. So while people are thinking about questions, I have a question myself about the application of this instrument. So can it be used for any kind of environment, different exposure levels, concentration levels? Does it work for very clean environments with
Yes,
as well?
absolutely.
So
Yes.
have it been used in that kind of really clean urban or rural environments as well?
We haven't. What we have been using it for, so we were using it for atmospheric measurements in China. Unfortunately, concentrations are not low there, so we have plenty of material. So the limitation may be that we can't, if we don't have enough ROSs that we can detect, we will not see the signal. So we will collect particles regardless of their concentration. The problem is if we can detect really low levels of ROSs. I haven't worked with let's say rural air, so everything that I was sampling, including different combustion sources or vehicle emissions or urban air, everything was toxic enough so that I could have a signal. But it can be a challenge, not necessarily that we can't do it.
So it worked well in urban area in Austria as well, where the exposure levels, the concentration levels are
Yes.
lower than China.
Yes, absolutely,
Great.
absolutely, yeah. Yeah, so this instrument can also be used just to collect particles into liquid, you know. So it can be just used to, let's say, as opposed to filters where you have to collect particles on filters and then analyze them later in the lab. Here you can directly sample particles of all sizes with high collection efficiency into the liquid medium. We can collect into the water as well. So it can later be used for, let's say, cell exposure studies, where these extracts can be directly used for the exposure.
Okay, we've got a question. Farhan, can you hear me?
Sure. Yes, I can hear you.
Here from Beijing. You go ahead.
Yeah, sure. It would be good if they can introduce themselves firstly. That would be good. Zoran, we can't really hear well. If it's possible, if they get closer to the microphone. Your voice is fine, but can't really hear her.
Hello, could you hear me better now?
It is much better. Yeah. Okay, thank you.
Great. I'm in June Liu. I'm a new faculty at School of Environmental Science Engineering at Peking University. So this is a great talk. I really like the deduct instrument. The question I have is, I understand that the purpose of the instrument is to measure the ROS from the particles. But you also mentioned you'd be able to actually have the measure ROS of the gas phase part.
Yes.
So I'm curious, how is what's the collection efficiency for the gas phase ROS? If there is some way to judge that part, and when you do real experiment in outdoor, so what's the how much is ROS from the gas phase part from your measurement, and how much from the total? Like what's the portion from the contribution from the gas phase?
Yes, thank you for your question. It's really interesting question. So we haven't done collection efficiency of different specific gaseous species, like let's say for different functionalities present in the gas phase, we haven't done that. So we have, we can collectively report the oxidative potential of the gas phase that we can collect. Now, we did experiments to estimate the collection efficiency of like the total VOC fraction, and we have the collection efficiency of that. We have to design and conduct experiments that will allow us to quantify the collection efficiency for specific organic species, let's say for carbonyls, for aromatics, for different types. We haven't done that. But as we have a huge, so gas phase is normally much higher than particle phase. The amount of ROS that we measure is much higher in the gas phase. So we are measuring it. The way we report it, we just report it per cubic meter, but we still need to work on that in order to make it representative of different species, so that once we have a number that we know how much potentially we can have of different functionalities.
So the simple answer is we don't know.
Well, you know, I have a feeling for that, but because I have seen my ROS gas phase signals, and I also had concentrations of different VOCs that we measured collecting in canisters and then analyzed, and based on the differences between these samples, I have a slight idea which VOC species we collect and which VOC species are not giving us any response. But we still need to confirm that with experiments, direct experiments.
Yeah.
Yeah.
Thank you.
Thanks, Svetlana. Any other questions? We have another 4 minutes, so we can take another question.
There's one more question here.
Fantastic. Yeah, go ahead.
Can you come closer?
Yeah. The first thing, do you think it's long-lived RS or short-lived RS, because you have a detection time around 14 to 16 seconds, right?
Yes, it is being subtracted from the signal that you see.
No, the question is it, do we measure the long-lived or the short-lived species? Because we have such a short response time.
Well, you know, I believe that we are measuring both. Depends, you know, if you are measuring the urban air, you are for sure measuring both, because we have mixture of fresh emissions and aged emissions. We are measuring both from direct sources. I think that we are measuring these again both, because we can measure long living ROS things. We can't separate them during our detection, because we are just measuring the total ROS, but I guess both of them are there, short living and long living. But in the aged atmospheres, we are just probably measuring the long living ROSs. Yeah.
Okay, thanks.
No,
Thank you.
You're welcome.
We may have time for another question if there is one more question. Any question?
I'm Professor here. I have a question about what is the major ROS species you are measuring?
I didn't hear. It just.
What's the main ROS species that we are measuring?
What are the main ROS species we are measuring? So we did some. We are measuring peroxyl radicals. We can measure hydroxyl radicals. We are measuring carbon-centered radicals, and sulfur-centered radicals.
Mm-hmm.
So we measure sulfur-centered radicals directly, nitrogen-centered radicals directly, and carbon-centered radicals directly. Oxygen-centered radicals we are measuring indirectly, because they are firstly reacting with the dimethyl sulfoxide, which is a solvent. After they react with the solvent is generating sulfur-centered radical that is then reacted reacting with the nitroxide, and then we detect.
So if the ambient samples is different, the RS species you are measuring is different because you measure the probe.
Yes, their mechanism is different, but what we have is that collective fluorescence response. But I was doing tests for 2 years with different species. I was exposing them to the probe and analyzing the mechanism. I can send you that paper. So I analyzed the mechanism, how the probe detects ROSs. And oxygenated species that are the most reactive, like short-living ones, they are reacting with the DMSO very fast, generating that sulfur adduct of DMSO that reacts with our probe in less than like parts of a second.
I have a short follow-up question. You have identified OOA has the most link with that. You have that EST paper. Do you have any plan to further identify this OOA using other methods?
Zoran, can you just, I heard half of the question.
Okay, so do we have, we've identified that the oxygenated organic aerosols in general
Yes.
are mainly responsible for the fluorescence.
Yes.
Do we have any plans to further look into which specific
Yes, we do.
OA species?
We do. I'm very interested in that. Yes.
In chamber studies?
That was the idea, and that was the idea behind the discovery project that we have, that we actually generate single species and that we age them, and that we track the ROS of different species, so that we inject like let's say one VOC, and then that we firstly see the ROS of that, and then that we see how it transforms, how it ages.
I see. Okay, thank you.
Thank you so much. Yes, thank you.
Thanks, Svetlana. Thanks for a great presentation, and thanks everyone for attending today's webinar, especially all the people from China. And thanks, Zoran, for organizing that. So we will conclude here, and I hope that you will all have a great day today.
Thank you.